Dear student, today we will discuss about electrical potential energy or interaction energy. First of all, what is the meaning of this statement? As it is mentioned here, electrical potential energy or interaction energy means when the two charged particles interact each other. Interact each other means one of the charged particle come into the influence of field of the other charged particle, then they will have some energy that is called interaction energy. For example, let suppose Q1 is one of the charged particle and another charged particle is your Q2. These two charged particles may be of same nature or may be of different or opposite nature. Let these two are same type of charged particle, means positively charged particle for example, and initially these two are at a certain distance. When these two release from rest, then what will happen? Because of the force of repulsion, these two charged particles acquire certain velocity. So now if we will see the system of these two charged particles, in the system of these two charged particles, any external force is not acting, then how these two charged particles has acquired certain velocity? It means there is some force acting or there is some loss of energy. Why? Because initially these two charged particles was at rest, they don't have any kinetic energy, but because of the force of repulsion they acquire certain velocity. Because of that they are having certain kinetic energy. So who is the or what is the source of that kinetic energy? If we are talking about a whole system, in the system external force is zero. It means from external none of the energy has come. It means there is some loss of energy, and that loss of energy convert into the kinetic energy of the charged particle. So it means there is some energy is there, and there is some energy is there, and that energy convert into the kinetic energy. So that energy is nothing, it is the interaction energy between the two charged particles, or we can say this is the internal energy of the system which has been decreased or which has lost, and that loss of energy convert into kinetic energy. So here we will discuss about that type of energy, what was the internal energy of the system was there, so and what is the source of that energy. So let's see here. For example, let's say here, let this is charge Q, and this Q charge is your fixed. Fixed means it is unable to move. And now if any charge Q naught I am bringing from here to here, slowly, if I am bringing this charge Q naught from one position to another position slowly, see, let this is the position 1, and when we brought this charge from position 1 to position 2, so what has to be done externally? If it means some external force is needed. What external force is needed? If the charged particle is at rest and keep free, so electrostatic force will act in this direction, and we are moving opposite to direction of electrostatic force. It means some external force has to do certain work to bring the charged particle from position 1 to position 2. So whatever work done by the charged particle, done on the charged particle by external agency, where that work has gone. So that work is nothing, it is the or that work convert into the internal energy of a system of these two charged particles. So there is an increase in the internal energy of a system, and that increase in the internal energy is nothing, it is the change in the potential energy of a system when charged particle has brought from position 1 to 2. Similarly, just opposite we can say, let charged particle is here and Q naught is this another charged particle, this is position 1, this is your fix. Now if this charged particle kept free free to move, then what will happen? Because of the electrostatic force, right now charged particle is here at position 1. After some time it may be in the position 2. So, and in this position 2 it has certain velocity. Then what can be said here? If we are again talking about this 2 charged particle as a system, so no external force is acting on the system. So, electrostatic force is doing certain work. Due to that work, this charged particle has acquired certain kinetic energy. It means there is a loss of some internal energy from position 1 to 2, and that loss of internal energy is nothing, it is the loss in potential energy of a system. So, there are two ways to define electrical potential energy or interaction energy. What are those two ways? One thing we can say, in the first situation when external force is acting against the electrostatic force, then their internal energy of a system or potential energy of a system increases. So, change in potential energy of a system is nothing, it is equal to work done by external force against electrostatic force. And but in the second situation, no external force is there. Because of the electrostatic force, charged particle is moving from position 1 to 2. Because of that work, this charged particle has acquired certain kinetic energy. So, there is a loss of that kinetic energy, means gain of kinetic energy means there is some loss of some other form of the energy. So, we can say change in potential energy of a system is nothing, it is negative of the work done by electrostatic force. So, in general we can define like this. So, we can define as change in potential energy or delta U is nothing, it is the work done by external force against electrostatic force or we can define change in potential energy is equal to negative of work done by electrostatic force So, we can say here delta U is nothing, work done by external force, and here delta U is equal to negative of work done by electrostatic force. So, in this manner we can define electrical potential energy or interaction energy of a system. Now, how to calculate the electrical potential energy of a two charge system? See, change in potential energy of two charge system. Let one charge is given Q, which is fixed, and another charge Q naught. This position of charge is your let 1. Now, we want to calculate change in potential energy from position 1 to position 2. Position 2 means that is your at a distance R2 from charge 2. See, so change in potential energy, it means delta U is nothing, final position 2 minus initial position 1. This is equal to, now work done by external force. or we can say negative of the work done by electrostatic force. So see how to calculate here. If we are using the change in potential energy as work done by external force, and that work done by external force against electrostatic force, see here. As we saw, when the charged particle is moving from position 1 to position 2, so the distance or the position of charged particle changes from the fixed charge q, and the electrostatic force is inversely proportional to the position square. So external force also we have to apply, which is variable. So we can solve by this way, F external to dr. Now how to calculate F external? Let at a certain position, when the charged particle q naught is at a distance r, so at this position we can write force q naught by r square, and since external force here in this direction, and we are also bringing the charged particle in this direction, dr. And since r is your decreasing, so here we can write here minus sign here, minus dr. Then integrate from position r1 to r2. Now simplify, delta use 1 by 4 pi epsilon naught q naught dr by r square here 1 by r. So 1 by r2 minus 1 by r1. This is the change in potential energy for 2 point u2 minus u1. Okay. Now this relation we can generalize. Okay, now this relation we can generalize like this. So as here position 1 is your at a distance r1 from the fixed charge, and position 2 is at a distance r2 from a fixed charge. See, since whenever we are calculating change in potential energy, normally we are defining a reference point. With respect to that reference point we are defining, and since it is also written as a interaction energy. Interaction energy means when the two charge interact each other, and the two charge will interact each other only when they will be at a finite distance, then only they can have some interaction energy. But when the charges are at infinite distance means there is no interaction, means none of the charge will come into the field of the other charge. So at infinite distance there is no interaction between the charge. So we can say there is no interaction energy when the charges are at infinite distance. So infinite position we can define as the reference point. So if R1 we are defining as infinity, here means first position we can say let infinity. So corresponding potential energy at 1 is written as u at infinity, and R2 is any finite distance, let R. So corresponding potential energy at that distance here written as u at R. Now we can substitute these values in this expression. So what we will get here, ur minus u infinity, this is equal to your R2 become here R, and R1 your infinity. So this relation will be your 1 by 4 pi epsilon naught q naught by R. So this is the general expression, and or we can say u r u infinity plus 1 by 4 pi epsilon naught q naught by R. So this is the potential energy or interaction energy of two charge system when the two charges are at a distance r, and this potential energy with respect to infinity. Sometime in certain problems they are defining the potential energy at infinity is this much, that value we can substitute here. Otherwise, normally interaction energy at infinity is 0. So, formally you can say normally U infinity is 0 or nothing is given in the question. So, we have to take U infinity as 0. So, UR is written as 1 by 4 pi epsilon naught Q naught by R. This is the interaction energy of two charge system when the two charges are at a distance r. Now, basic points related to the interaction energy. Now, see the first point. As potential energy is your scalar quantity, if potential energy is scalar quantity, so in this expression the value of charges Q and Q naught has to be kept with their respective sign. So, we can write, since potential energy is a scalar quantity, so charge values has to be kept with their respective sign. Second point, it follows the principle of superposition. Principle of superposition, meaning of this, the potential energy of a system does not depends on the presence of other charges. For example, let we are having number of point charges or number of charges Q1, Q2, Q3 likewise. So, distance between Q and Q1 is let R1, Q and Q2 R2, Q and Q3 R3. And if we want to find interaction energy of a system, so interaction energy of a system with respect to infinity, see, it is just like nothing. We are bringing one by one charge together here. See, we can say like this, initially there is only Q charge was there. Now, when we are bringing charge Q1 from infinity to R1 distance, so how much the interaction energy between the charge Q and Q1? From here we can say Q naught by R. So, similarly Q1 by R1. Q1 by R1. Now here two charges are there. One is Q, another is Q1. Now, if I am bringing the another charge Q2 from infinity, so now when the Q2 charge will come, that charge will come into the effect of or into the influence of electric field produced by the charge Q and Q1. The C. So, when it comes or when it will come under the influence of charge Q, then we can say Q2 by R2, and simultaneously it is coming under the influence of charge Q1 also. So, if separation between the Q1 and Q2 let R12, then another term will come that give you the interaction energy between the charge Q1 and Q2. This will be written like this. Now we are having three charges in the system, Q, Q1 and Q2. Another charge Q3 is coming now. When the Q3 will come from infinity, so it will come under the influence of or under the electric field of charge Q, then under the electric field of charge Q1, then under the electric field of charge Q2, means each and every charge will produce their own effect. So, due to that own effect, they are having own interaction energy. So, effect of Q on Q3, that we can write in that form Q3 by R3. Now, it will come under the influence of electric field of charge Q1. So, 1, 2, 3, this is your 1, 3 we can say. So, plus 1 by 4 pi epsilon naught Q1 Q3 by R13. Similarly, it will come into the influence of charge Q2. Then we can write interaction energy between the charge Q2 and Q3 written as R23 like this. So, this is the total energy of a system, and that is also called energy of discrete charge system. It also can be said as a energy of discrete charge system like this. It means if we are having more than two charges, so what we will do, we will calculate the interaction energy of individual charge system. So, presence of, so according to the principle of superposition, so we can say each and every pair of charge energy will remain same. It does not depend on the presence of other charges. So, this is the meaning of principle of superposition. Now, see, we can see this thing, or we can discuss this point with a certain one or two example, then it will be more clear. Let us see one example. Let three charges are kept at the corner of a equilateral triangle. One of the charges Q, another let minus 2Q, and here let your 3Q, kept at the corner of an equilateral triangle like this. And now the question is that what is the work done to remove one of the charge, let 3Q charge from the vertex of the triangle to the infinity. So, once again, let three charges kept at the corner of a equilateral triangle of side L. Find the work done to remove charge 3Q from vertex to infinity. Let this is the question here. Work done. So, the question is that three charges kept at the corner of an equilateral triangle of side L. Find the work done to remove charge 3Q from vertex to infinity. So, what we will do, as we have defined the interaction energy is nothing, total work done by external force is equal to change in potential energy. So, first we will calculate what is the initial interaction energy, and after removing 3Q charge, what is the final interaction energy. So, let initial interaction energy. So, we can define that this is charge number 1, 2 and 3. So, initial energy is nothing, interaction energy between charge 1 and 2, that we can say interaction energy between 1 and 2 means U12. Similarly, interaction energy between 1 and 3, so that we can write U13 plus interaction energy between 2 and 3, then we can write U23. Now, this value we can calculate U12 that can be written as 1 by 4 pi epsilon naught, that we can say common because that term will come in all the expression. 1 2 3Q square by L, 1 3 negative charge. So, it becomes your minus 2Q square by L, 2 3 negative sign, minus 6Q square by L. So, the total value will be here minus 1 by 4 pi epsilon naught 5Q square by L. This is the initial interaction energy of a 3 charge system when the charges are at their vertex of an equilateral triangle. Now question is this: if 3q charge has been taken to infinity, so when this reaches to infinity, this charge will not have any interaction with the charge number 1 as well as with the charge number 3. So only 2 charge left in our system, and these 2 charges are nothing, 1 and 3. So then the final interaction energy means interaction energy between the 1 and 3, and 1 and 3 means here only U13. U13 term will come here, minus of 1 by 4 pi epsilon naught 2q square by L. This is the interaction energy final. Now important point, work done. The first we will calculate change in potential energy. Change in potential energy means U final minus U initial. The U final minus U initial. So after doing U final minus U initial, we will get 1 by 4 pi epsilon naught 3q square by L. So this is the change in potential energy, and as per our definition, or we can say whenever final potential energy is more than the initial potential energy, then the change in potential energy will come positive. So positive change indicates who has done work on the system, means external agent has done on a system. That's why potential energy of a system increases. If in any of the certain problem, suppose change in potential energy comes negative, it means potential energy negative means final potential energy less than the initial. So it means energy of the system has been lost. It means system has done work. Okay. So from here we can get the whenever change in potential energy come positive, it means the work has been done by the external agent on the system, and whenever change in potential energy comes negative, it means work has been done by the system. Okay. So this is the one of the example. Example 2. In this example, we are having 2 charges Q and 2Q. Initially these 2 charges are very far away. Okay. Very far away means we can say the distance between these 2 charges are at infinity. One charge have value q, mass m, another charge have value q and mass 2m. So initially these 2 kept at very far away. It means there was no interaction between these 2 charges. Now what is the question here? Let charge q is projected towards another charge of mass 2m, and this charge is projected with velocity 2v in the first charge, like this. So question is that find the minimum distance between these 2 charges. So we can write the question like this: 2 charges, 2 charge having charge q and mass m and 2m are kept very far away. As shown in diagram. As shown in diagram, charge of mass m and charge of mass 2m given velocity v and 2v towards each other respectively. Towards each other respectively, find the minimum separation between the two charges. Minimum separation between the two charges. Now, this is the question. It means two charges, charge have equal value but masses are different. Given a velocity v and 2v towards each other, and now find the minimum separation between the two charges. So first, before solving the problem, we will see the analysis of the question. When the charge q given velocity v and this is also given velocity 2v towards each other, initially these two are at very far away, it means infinite distance. Due to the velocity when these two charges start coming close to each other. When these two charges start coming close to each other, so interaction between the charges start. So when interaction charge start, so what will happen here? The force on charge start acting. So let at a certain distance or after a certain time, this charge is suppose somewhere here and this charge is suppose somewhere here. In that case, what will happen? Force on this charger in this direction, force on this charger in this direction, because both are positively charged, force of repulsion. Because of the force, velocity of these charges start decreasing. So velocity of these charges will not remain same as earlier. Since, important point here, since the force between the two charges are equal in magnitude, so now what we will see, this force is the retarding force this charge and mass of this charge your 2m. So what is the retardation? The retardation on this charge is your F by 2m, while retardation on this is your F by m. So what has been observed from here, the retardation on this charge is your more as compared to retardation on this charge, and this charge have more velocity even. It means before this charge, or see, it means what we can say, since here this charge have more velocity and less retardation as compared to this charge, less velocity and more retardation, so this charge first come to rest, and that is not the final rest position. Instantaneously it come to rest. As soon as instantaneously it comes to rest, because of the force acting the leftward side, this charge start moving in this direction. See the meaning of that. See. So due to that force, it start moving in this direction. Now the force on this and velocity on this in the same direction, but force on this is still in the opposite direction. So one stage will come when the velocity of this and this are same in the same direction. After that, the separation between these two will increases. So at minimum separation point, this charge have let velocity or u, and this charge second one also have velocity u, and at this position let the distance between these two your r, and if we are talking about the force on this is still acting in this direction, but force on this here is acting in this direction. So from here, what is the conclusion is this? Due to the force and velocity in same direction, this will move with a faster speed now, and speed of this charge here further decreases. So gap between the charges here increases. So what is the conclusion from this analysis? Conclusion is that the charges will have minimum velocity only when, minimum separation only when both of them are moving in the same direction with the same velocity. So this is the main analysis. Now how to convert or how to solve this problem, or how to calculate analytically here. The first important point. First important point is this: if we are talking about this two charge system, in this system electrostatic forces are acting on individual charges, and since electrostatic forces are equal and opposite, the net force on a system is your 0. Convert, or we can conserve linear momentum. So first equation we can make by conserving linear momentum. The linear momentum is, if we are considering that is the positive direction, this is your negative direction. So according to the conservation of linear momentum, so initial linear momentum in P initial is equal to your P final. Initial means when these two charges were at infinity. So this has linear momentum your m into v in the right side. So right side means we are taking positive m into v, and this have linear momentum in left side. So that we will take negative, and velocity 2v and mass 2m, so minus 4mv is equal to final. Final, this have mass m and this have mass 2m, both are in the same direction, so minus mu and minus 2mu. So minus mu minus 2mu, so u will be here your v. So this is the means velocity. It means when both have velocity v in the leftward direction, then the separation between these two here. This is your first principle by from conservation of momentum. Second equation is that if we are looking the system, in the system no external force is there, so total energy of a system remain conserved by conservation of mechanical energy. So initial energy means when these two are at very far away. So initially when these two are very far away, there is no interaction energy, only kinetic energy. The kinetic energy of first half mv square plus kinetic energy of second particle half mass 2m and velocity 2v square. This is equal to final is this situation when kinetic energy, so kinetic energy in the final half m u square plus half 2m u square plus potential energy at r distance, that is the potential energy maximum potential energy when these two are at minimum separation. So 1 by 4 pi epsilon naught q into q in q square by r. This is your, we can say, second equation. Now substitute the value of u is equal to v here, then we will get the r value. So just check it, how much value we will get. This is your 8 plus 1 9 by 2 mv square, and u is equal to your v. So v square and v square 2 and 3 by 2 mv square plus q square by 4 pi epsilon naught r. So from here we can calculate the value of r. So r will be, bring 3 in this side, it becomes your 6 by 2. 6 by 2 means 3. So q square by 12 pi epsilon naught m into v square. This is the minimum distance between the two charged particles when these two are projected from infinity as shown in the question here. This is the second example. Now see next example, example number 3. It is given as find the self energy of a uniformly charged conducting shell of radius r. Conducting shell of radius r. Radius r having charge q. Having charge q. It means, meaning of this, this is your conducting shell of radius r and it has given a charge q. So, they are asking how much is the energy of this shell. It means they are asking the either self energy or we can say interaction energy of a cell. Let's see. First of all, what is the source of energy? Okay, as we know, when a charge is given to a body, it has some additional energy, that is called interaction energy or self energy. But how that energy has come? See, whatever q charge we are giving, that q charge is nothing, it is the removal of electron. So, when we are removing electron, so on this shell charge will come. Let analysis is this. Initially this shell was your neutral. Initially this shell was neutral. Now when we are making this shell as a charged shell, so what we are doing? We are removing electron. We are removing electron. As one of the electron removed, so this shell become your positively charged. So positively charged shell and electron removal, there is a force act on this electron and that force is the force of attraction. This is your electrostatic force we can say. But we have to remove, so we have to apply the force opposite to direction of electrostatic force, and that force we have, since electrostatic force will act up to infinity, so we have to apply external force up to infinity. So whatever work I did to remove the electrons from surface to infinity, that work is stored as electrostatic energy of a shell, and that is called your self energy of this shell, charged cell, or we can say potential energy of a shell. Let's see, since external force when we are applying, that external force here opposite to electrostatic force, and as distance changes, electrostatic force will change. So we have to again integrate. So let at any time charge on the shell is q, and we are removing dq amount of charge. At a certain distance, r is this. Now, since electrostatic dq charge we are removing, so we have to apply external force in this side. So work done to displace charge r to dr. So that work done is written as F external into dr, and F external at this position must be equal to the electrostatic force. So which is equal to 1 by 4 pi epsilon naught q dq, because q charge already there on the surface and dq charge we have to remove. The q dq means force between the shell and this dq by r square into dr. Now total work done to remove dq charge, that work done is written as dr by r square, and we have to remove from where? From surface to infinity. So range or limit will be from r to infinity. So this is nothing 1 by 4 pi epsilon naught q dq by capital R. Now, this is the work done to remove dq charge. And how much charge total we have to remove? Total charge q we have to remove. So, total work that will be your 1 by 4 pi epsilon naught q dq 0 to capital Q by R. So, this become your q square by 8 pi epsilon naught R. This is the total work done, and this work has been done by external. So, this is the self energy of a cell. This is also known as self energy of a cell, and self energy of a cell is given as q square by 8 pi epsilon naught R, or this can be said as a U. It's very important term relation here. This is the self energy of a cell, q square by 8 pi epsilon naught R. Now, see another example. Find the self energy of uniformly charged non-conducting sphere. So, here we can assume let q is the charge on a sphere and r is the radius of a sphere. See, the meaning of this question is, or statement is this, non-conducting sphere. Important point here, non-conducting sphere. The non-conducting sphere means total charge is uniformly distributed throughout its volume. It means if we are giving a charge q, so this charge will be spread throughout its volume. This. So, if r is the radius and charge is q, so we can write here volume charge density rho is equal to q by 4 by 3 pi r cube, or rho is your 3 q by 4 pi r cube. Now, important point here, first analysis of the problem. It means what we have to do in this, or how the energy has come. So, we can assume we are making a sphere of radius r by putting a number of concentric cell one over another. It means let this your one shell and some charge is given to this shell, then another shell, some more charge given to this shell, then third shell, like this. And all these concentric cell when combined make a complete sphere of radius r. And due to the shell, already we have calculated what is the self energy. So, here also. So, what we can say, we can assume a shell of radius r and dr thickness. See, let this your complete sphere, and in this sphere we can assume a shell of radius r and dr thickness. So, whatever charge on this shell, that charge is let dq. So, due to this dq charge, how much energy? The first, how much charge? dq. dq is here nothing, charge per unit volume or volume charge density rho into volume of this part The volume of this part is your 4 pi r square into dr. This is the charge on this shell. Okay, and then we can calculate how much the energy is stored in this, and we have to integrate further. Or another way is that we can calculate total charge on this shell, and then we are removing the charge dq. This is the one. Another method is that, see, okay, this is the charge on this shell, and how much charge kept here in this part? In this part, let charge is your q. So that q is nothing, rho into 4 by 3 pi r cube. This is the charge on this part of shell q, and dq is the charge on this. Now, what we are doing, this dq amount of electron we are removing and bringing from surface to infinity. So, work done we will calculate. See the work done. So, total work done is written as F dot dr. So, F is your 1 by 4 pi epsilon naught q dq. At certain time, the distance between this charge and this charge is let x square, and we are removing and bringing this dx. Now, so 1 by 4 pi epsilon naught limit, x limit your from r to infinity. So, it will be your q dq by r. This is the work done to remove the charge from surface to infinity. Now, work done due to all charges. Work done due to all charge. 1 by 4 pi epsilon naught. Now, substitute the value of q. Q is your rho 4 by 3 pi r cube, and dq value rho 4 pi r square dr by r. And now, we are charge means from 0 to capital R. And after that, substitute all values. So, you will get here 3q square by 20 pi epsilon naught r after integration. So, this is the work done to make this neutral sphere into a charge sphere of having charge q, and this is nothing, it is the interaction energy or self energy of a non-conducting sphere. Self energy of non-conducting charge sphere. So, these are the very important relation, and this relation we have to use here. This is the one relation, and the previous case we have found self energy of a spherical cell is given as q square by 8 pi epsilon naught r. So, these two relations we have to remember, because that is very useful in the next question here. So, this is the self energy of a charge sphere. Now, come to the next problem. For next problem, we can write, there are two relations which will be useful. First is the self energy of charge spherical shell. Charge spherical shell, it means this is your shell having charge q on its surface, and radius is your r. So, their self energy is, as we have calculated earlier, 8 pi epsilon naught r. This is self energy of a charge spherical shell. Now, second relation that you have to remember, the self energy of charge non-conducting sphere. Non-conducting sphere, it means this is your sphere and throughout its volume charge is given and r is the radius of this total charge at q. So, then the self energy of this will be 3 q square by 20 pi epsilon naught r. So, these two relation is very useful. Now, see how these two relation can be used in the next example. So, the question is this: a spherical shell having a charge q and radius r. A spherical shell having charge q and radius r1. A point charge q naught kept at the center of shell because of this charge radius of shell becomes R1 to R2. Find the work done by electrostatic force in this process. Electrostatic force in this process. This is the question. Question is very simple. It is given q charge is distributed on the surface of a shell like this and q naught charge kept at the center. So, what will happen due to this charge q and q naught? There is a force of repulsion. Due to the force of repulsion, this shell will expand and now it becomes a shell becomes of radius r2. So, now you will have to find how much is the work done in this process. It means in the expansion of shell, how much work has been done. So, here also there are two ways. Work done is nothing, it is the change in interaction energy or change in potential energy of a system. See, first we will calculate the work done in the first system or when the radius was r1, and then we will calculate the work done when the radius is your r2. See, so what is the effect of that? Due to the presence of q naught charge, we can get induced charge inside the shell. That charge your minus q naught. So, outside of the shell to oppose that one plus q naught will come. Similarly, when the radius your r2, here also same thing will happen. Minus q naught will induce inside the shell, outside it will be your q naught, that's all. So, we can have, there are two surfaces, one inner surface, another your outer surface. So, when we are talking about interaction energy, initial energy means interaction energy between q naught and inner surface, q naught and outer surface. And since distance of inner and outer surface are same, because we are considering shell, we are considering shell, so thickness of shell is negligible, so there is no difference in the keeping the inner and outer shell surface are the same surface, because the thickness is negligible. If there is thickness is given, then we have to take the separate interaction energy between the point charge Q naught and inner surface charge, and point charge Q naught and outer surface charge. But here, since the thickness of shell is negligible, so whole surface can be taken as a single surface. So the net charge on that single surface is your Q only. So first of all, interaction energy between the charge Q naught and surface charge. So 1 by 4 pi epsilon naught Q naught into Q by R1. This is the interaction energy between the charge Q naught and the charge on the surface of cell. Second energy means when charge Q was there on the surface, so that due to that charge it has some self energy, and that energy is nothing Q square by 8 pi epsilon naught R1, as we have calculated here. The energy due to the charge Q, self energy, or Q square by 8 pi epsilon naught R, that relation we can write here also. So this is the initial energy when the charge Q was given on the shell. Now, because of the force of repulsion, when the radius or distance between the center and the surface is your R2, in the same way we can calculate the self energy as well as interaction energy. So now interaction energy will be your 1 by 4 pi epsilon naught Q naught Q by R2 plus self energy or Q square by 8 pi epsilon naught R2. So work done in this process. So work done is equal to your delta U, it means U final minus U initial, and now simplify this. So 1 by 4 pi epsilon naught Q naught 1 by R2 minus 1 by R1, and in the second expression will be your Q square by 8 pi epsilon naught 1 by R2 minus 1 by R1. So from here we can see here R2 value or more than the R1 value, the whole term will be your negative, this term will be also your negative. So change in potential energy or negative, so that indicate work has been done by the system. It means system energy or decreases due to the expansion of the cell. This is the one of the example. So these are the some basic example related to the electrical potential energy or interaction energy and their relation. Now come to the next topic, electric potential.